So in the previous video, we introduced the concept of chemical formulas. Chemical formulas involve the element symbol and a subscript to denote number of element present. And we said that chemical compounds can be ionic or molecular covalent. But let's further subdivide chemical formulas into particular types of chemical formulas that you will see throughout your chemistry career in this course and beyond. So the formulas that we have talked about so far can be classified as molecular formulas. That means it gives you the exact precise number of atoms for an element that are present for that particular molecule. For example, if I was to analyze the glucose or the sugar that was in my coffee, if I was looking at specifically glucose, I would find that one glucose molecule contains 6 carbons, 12 hydrogens, and 6 oxygens. That is a molecular formula. That's what's actually present in that molecule of glucose. But hopefully you can see that looking at that molecular formula, you see that you could further subdivide or simplify that formula into something that's called an empirical formula. Empirical formulas are the simplest whole number ratio of atoms in a particular compound. Now you may wonder, well, why do we care about empirical formulas if that's not what actually is present? You know, one molecule of glucose doesn't have just 1 carbon, 2 hydrogens, and 1 oxygen, although that would be the empirical formula. You can divide all of those subscripts by 6. But as we'll find out in Chapter 3, empirical formulas are really important to chemists because oftentimes when chemists are identifying a brand new compound or trying to determine the identity of an unknown, they will do experiments that can easily determine its empirical formula, its simplest whole number ratio of atoms in a compound. And then from other data can determine its actual molecular formula. So take-home point, I know I keep saying that, take-home point from this slide, empirical formula, simplest whole number ratio of atoms in a molecule, in a compound, that is different than the molecular formula, the exact number of atoms that are actually found in nature in a particular compound. So in our last slide for types of formulas, we're going to talk about the importance of structural formulas. So if you go on in chemistry, you'll study a lot about, in more detail than you will in this class, you'll study about how to draw molecules with regards to how the shape of that molecule comes about. For example, let's say I have CH4. This is the molecular formula of CH4. I've got 1 carbon and 4 hydrogens. That's very important information. But that molecular formula does not tell me anything as to how those 5 atoms are connected to each other. It's only through a structural formula that I know how those atoms are actually connected to each other. And depending on the type of model that you look at, those models can also tell you the shape of the molecule that occurs due to those connections. Now later on in the course, we're going to talk about something called Lewis dot structures and how we can use those to say something about the geometry of smaller molecules. But as you go on in chemistry and these molecules get bigger, you will use structural formulas like a perspective drawing or a space-filling model, so you can actually have a sense as to how big a molecule is and what its shape and size are. For right now, just know the difference between structural and molecular formulas. Molecular formulas tell us the actual number and type of atom in a molecule, but the structural formula actually speaks to the shape and the connections that are made between atoms in a molecule.